printing work now. And the thing we have still to do is to see what threads are and then see how threads are combined with blocks. Okay, so we said that there are two layers of parallelism, and we saw one, which is blocks. I'm going to show how threads are used without explaining why they are needed. And only when we combine them, I'm going to explain actually why threads are also needed. Why can't we just use blocks? Because naively, you could say, you've already given me a way to run parallelly whatever number of blocks I need. So why do I need threads as well? So we're going to answer that later, but first of all, I'm going to show you what threads are and how they're used practically. So this is going to be the kernel now. This is a kernel that uses only threads. And notice that it's really similar to the last one. Guys, be with me, please. But now the magic variable is not called threadID.x, it's called blockID. It's not called blockID.x, it's called threadID.x. That's another magic variable. So since there are two layers of parallelism, there are two magic variables, blockID and threadID. And this, without explaining why it's done, only how it's done. This is how it's done. There is a magic variable called threadID. And because earlier we used no threads, the number of threads was set to 1, there was only one threadID and we didn't need to use it. And now we're going to use more than one thread ID.
Block is like node, play like a node.
We don't do that right now.
Yeah, but it is...
No.
What is grid and what is block? Grid is the older device?
Now, grid is the collection of blocks. I'm gonna go through it, and then when we have both blocks and threads, I'm gonna do some order. Okay, make some order. So contain your confusion for now. This is the thread ID, the magic variable thread ID. The changes that we need... What?
We can just replace and recompile?
Almost. We need to make one more change. One more change, because you see the fact that you use here a thread ID, that's all very nice, but you need to tell someone how many threads to put, right? And this is done in main. The main is actually the same as before, only now it's exactly same as before, only before it was n and then 1. And now it's 1, n. We switch the order. Now we are running it with one block but n threads. Okay? So again, this doesn't make sense. Why do we have two layers? And why are we running just one of these layers? If there are two layers, there must be a reason. Let's run with... So, slowly. But this is all the changes that are needed in order to run with n threads. And again, the idea is this. There is some entity, a scheduler, that makes it so that each time the kernel is reached by a physical core on the device, the magic variable threadID.x has a different value between 0 and 511. And that's why each core adds a different index and the job is done. Okay? So, why two layers of parallelism? It takes more than a minute to answer it accurately. Okay, but I'm going to answer it inaccurately for a while, and then we're going to get it more accurate. The inaccurate answer is that when you're going to have 2,000 threads running in parallel on the machine, those threads are not uniformly distributed. They are not completely equal. They actually run in groups. The threads run in a group. And threads that belong to the same group can do things together. They can share information. They can share data. They can synchronize. Okay? Within a group of threads, threads can cooperate. And this group of threads that can cooperate is called a block. Okay? A block is a group of threads that can cooperate. What is cooperation? We'll see later. Threads between different blocks, threads of two different blocks cannot cooperate. They cannot share information, they can't synchronize, they can't ask each other how they are, or have they reached a certain line of code yet? They can't. But threads within a certain block can. And this is why we have two layers of parallelism. You tell the code how many threads are in a group. The group is a block. And then you tell it how many blocks in total are needed. And the reason for it we'll see later. But these are the two layers. So, we're going now to see how to use blocks and threads. We're going to still add a vector because this is all we do, right? But now we need to see how the indexing works, because we've seen that the only magic of CUDA is enabling us to write really simple C code, but magically giving us the index. This is the whole thing. You get the index. And now we have two indexes. We have the thread ID and we have the block ID. Two magic numbers, and we have to fit them into a single index. And this is how it's done. Let's say this is an unrealistic example that in each block we put 8 threads. Okay? So this is the first block, and it has 8 threads from 0 to 7. The second block, block number 1, also have 8 threads from 0 to 7, etc., 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 etc. And now what we need to do is we need to get into a situation where we have an index and each thread block knows which index it's going to add. We need to get to a point where, okay, ignore the second line, the first line, sorry. The second line is in the end we're still going to have to do C index equals A index plus B index. We're still going to get the index from somewhere. It just now it's going to be slightly more complicated. And this is how it's done. This is the division of blocks and threads. And a very simple way of making them create our final index is this. The index we're going to work on the vector equals this thread ID plus the block dimension, this is another magic variables, times m. The block dimension, the block ID times m. M is here 8. This size. Yeah, this size. 8. Right? So this creates a very simple mapping. You take the number of the block times 8. That gives you sort of the starting point of each block. And inside the block, you move forward by thread ID. Right? You get each index in the array once, this way.
Why?
Why?
Block index
Yeah.
has m threads. Every block has m threads.
Yes.
So what I need to do with this thread index? It is the index.
This is the index. This is the index inside the block. This is the index of the block. And this is the index that I'm going to operate on in the data. This is the index in the data. Take a look at the next slide. This is the index in the data, right? This is my vector. This is the index in the data. And the question is, let's say for this element, which is the number 21st element, which block ID and thread ID are going to work on it?
Block 3. 3.
Yeah, so it's actually number 2 because it starts from 0. So the first block is going to work on the first 8 threads. Second block arrives at 15, and my value, which is 21, is the 5th thread of the third block, which is number 2. So block number 2, thread number 5. This is what we get. Okay?
Map to actual cores.
I can't hear you.
How is it mapped?
To what?
How is it mapped actually to physical cores?
Not only that we didn't talk about it, we will not talk about it. Okay, so do you understand why this mapping, this is the index that we're going to operate on, and these are the magic variables, and in order to make sort of a transition from the magic variables into the index that we're going to work on, this is the transformation. Is that okay?
It is the reminder, the 5. It's what remains in the last block.
This is the thread ID. Yeah, it's the index of the block that is in question.
grids contain some elements?
No, there is no elements here. It's just numbers. So far, only number.
5 is the index of the thread in the last block.
What is the last block? It's not the last block. It's this block.
Block number 2,
Yeah.
index 2. Block has index 2.
Yes.
So number 5 is the index in the block number 2.
Okay.
0, 1, 2.
Okay, you're using a framing that is hard for me to follow. It works this way. The question here is what block ID and thread ID are going to deal with element number 21. And the answer is it's going to be the 5th thread in block number 2. Is that okay? Yeah.
So it's kind of pointer?
It's not a pointer, it's just numbers so far. These are magic numbers and I'm making an index out of them. That's it. And now, obviously, I'm going to work on this index.
This element is element 21.
Yeah, you're right. It's element number 21. It's the 22nd element. Yeah. You're right. It's number 21. No, it starts from 0.
How did you get M?
You started index 0.
Soon.
So it's not index from 0, 0.
It's 22nd element, but it's index
M
21.
is the length.
Are you okay? Okay. So, guys, in order to be able to calculate this index, I'm going to need this M. How many threads are in a single block? This is sort of a constant, right?
Where do you get this info? Is it something you can define, or is it something?
It's a wonderful thing that we have a presentation with more than one slide. It might be in the next.
You never know.
You never know. So this is actually, it might be in the next. I know it's confusing. Let's try to ask a few less questions now. I hope it's going to be clear in 5 minutes. Okay? So this is the actual code. Okay? Index equals thread ID x plus the block ID, and I'm not going to multiply it by m now. What is m? It's going to be multiplied by another magic number, which is block dimension. Block dim is block dimension x. So this is our 8. And this is, again, a number that is available within the kernel. And now that I have produced my index, from the magic number, I have produced an index, and I can operate on that index. That's it. You have a thread ID and a block ID, which are distributed by a scheduler on the GPU. From them, you create an index on the data on which you want to work, and then you do whatever operation on this index. Why is it parallel? Because different instantiations, different occurrences of this line will get different magic numbers and therefore would operate on different indexes of the data. Parallelism. Okay? What do we need to do in main? So now we do threads and blocks.
Change the code.
This is unchanged. Okay, this is unchanged. This is changed. What is written here inside these strange parentheses? We run a certain number of threads per block. It's defined up there. I don't remember what was it. Oh, now, okay, look. Now we are running 4 megabytes of data. N is much larger now, and we have 500 threads per block in this one. And so here we are running, just a sec, not in the middle of the sentence, please. So 500 threads per block. And how many blocks do we need to run? Does that number make any sense? Why are we dividing it? Yeah, it makes sense? Exactly, because the multiplication of this by this should be the number of elements.
So what is the difference between block and thread? You can convert the definition and it will be the same.
Absolutely not.
Why?
Again, very lucky that we have more slides. So just one sec. So is that clear? Is that clear? We have both threads and blocks right now, and as I said before, those threads can cooperate. Those are in a single group, 512 in this example. These 512 threads can cooperate. They can share data. They can synchronize themselves. This is how many threads are in a group, a block. And in parallel, groups of 512 threads are launched, many of them in parallel, and these are the blocks. Okay? So let me tell you something. Let me ask you.
You said before that threads are within a block.
Yeah, threads are within a block.
You say that blocks are within a thread.
No, threads are within a block. How many threads are in a block? This is how many threads are in a block. So threads are in a block. Okay? So, take a look at this and let me know, tell me, what is this? Block.x, what do you think is the value here? 512. And this is the 512.
It's how many threads?
Oops, where is it gone?
Block.
In the next presentation.
Oh, I'm running the wrong direction.
How many threads in all blocks?
It comes from here. This is this 512, because I've told it that there are 512 threads in a block. Okay? And then it reappears magically inside the kernel as block dimension.x. Okay, so let's first try to see if we agree that doing it this way gets us the same end result. We have created a mapping between the thread ID and the block ID to an index, and then we each time this line of actual operation is called, it has the same index. We end up adding all the vector. This is okay? And the way we've done it is by putting both threads and blocks. Now, I will not be able to tell you anything about how this maps to hardware, okay? But there is a lot of complexity here. How many, for example, here, there are 512 threads in a block. Let's say our card only has 200 cores. So how can 512 threads run on 200 cores? That doesn't make sense. And anyways, in this example, we have really lots of threads, blocks. We have thousands of blocks. We don't have thousands of cores. So how can they run in parallel? It's something strange here. Okay? So again, we cannot really cover it now. But the way it's mapped is that threads that are in the same block are mapped to cores that are close together. This is why they can cooperate and synchronize. Okay? And different blocks can sometimes run in cores that are far apart and cannot share any data. They don't know nothing about each other. And this is why we have these two levels of parallelism. The only thing that I didn't tell you is why would threads want to cooperate? What is this concept of threads cooperating? Okay? Is that okay that if I now only show you why some threads want to cooperate, then this double layer of parallelism makes sense, right? Mm-hmm. Okay. When we launch the kernel, okay, we've done this division. We had to. This division is very nice, but what if it doesn't really divide? What if there is a reminder? That's not so nice. Okay? What happens is that that's not so nice either. What happens is I can't actually launch separate threads. I launch groups of threads, and each group has a fixed size. And the number of the maximum index that I'm going to get inside the kernel, the maximum index that I get is this multiplication. The multiplication of this is the maximum index that I'm going to get inside. And if it divides, that's wonderful, but what if it doesn't divide? First of all, integer division rounds down. So if I round down, if I have 4 mega elements and 1, and I divide it this way, I'm only going to get the maximum index inside my kernel is going to be 4 megabytes. I left 1 out. So I can round up, right? I can round up. But if I round up, I get indexes that are out of the scope of my vector.
You should take care of the reminder separately.
So the way it's dealt with is this. I calculate this index because I have no other choice. This is the index that I can calculate. But I have this if. If index, only if index is smaller than n, do I make my operations? This is a really funny thing about GPUs. Since you don't launch single threads, but groups of threads, maybe the size of the data doesn't divide with my group size. And so you have to put this protection. If you don't, you'll know it. Okay? Get used to it. And this is the kernel launch. This is the way to round up. This is rounding up instead of rounding down. It's mathematical. So, why bother with threads? I've said it before. They add a level of complexity. It doesn't make sense. What do we gain? And the thing is that, like I said, threads can communicate with each other, share data with each other, synchronize with each other. Okay? In order to really convince you that it's necessary, I need an example in which it's necessary. Okay? So let's see how much time we have. We do not have much time. Okay.
This index calculations, does it cost you anything? It slows you down?
Theoretically it could. It normally really doesn't. Practically it doesn't. Okay, let me leave it at that. Otherwise it's a lengthy explanation. Okay, so how can threads cooperate and why would I want them to cooperate? So this is a more advanced thing, and we're going to go over it. We don't have much time. I want to give you a break before the closing remarks. So I'll rush over it a bit, and just to give you the concept, because I want to convince you that it's necessary. This is an example of a 1D convolution. Do you all know what is a convolution?
It's like a filter?
It's like a filter. Let's make it simple. I think they have. What we want is we have a 1D vector on the input, and what we want to do is compute the output vector. In the output vector, this is in, and in the output vector, each element is, let's say, the sum of these elements around it. And here we can use a radius of 3. Okay? This is the operation we want to do now. It can be an average, it can be some linear combination of them, whatever. It's a sort of one-dimensional filter. So let's say that each thread in a block is going to calculate one output pixel value. How many input pixel values does it need in order to calculate this one output pixel? 7 itself and 3 to each side. So it needs to read 7 input values in order to produce just one output value, right? Okay. And this is the way it looks in memory. I think they made an error. I don't know what this is for. But if you want to calculate these output values, you need to load these input values. Yeah, there is 3 on each side that you need to, it's called a halo. You need to load a halo on each side. So let's see how this is done. Okay, let's first talk about why it's problematic. We said each thread needs to load 7 input values. That sounds a bit wasteful, right? Because this thread is going to need to load these values. They almost overlap. 6 of these 7 values overlap. Why would I let these 2 threads go to the global memory twice in order to fetch these values? It's expensive bandwidth operation to my memory.
You can reuse the data.
Exactly. I can, if these threads can share the data, that would be lovely, because then maybe not only these 2 can share the data, maybe all these can share the data. And then instead of bringing x7 times data in order to compute my output, I can bring much less. Maybe I can bring each element only once. And this is it. This is this drawing. In order to compute one output element, I need 7 input elements. But in order to compute 1, 2, 3, 4, 5, 6, 7, 8, 9 output elements, I only need 9 plus 3 plus 3. The waste is less. Is that okay? The only thing I need for that is for the thread to be able to communicate. And this is how it's done. There is an onboard memory that is called shared memory. underscore underscore, shared underscore underscore. This is a physical memory. It's not just virtual. It's a physical memory that sits very, very close on the core. It's small, but it's very, very fast. It's like a cache, but shared memory is a manual cache. You manage it explicitly. It's not a magical cache that just stores your data for you. Okay? It's a manual cache. And when you declare a shared memory buffer inside a kernel, all the threads in this block see it. Which threads see it? Only the threads in the same block. Why? Because only the threads in the same block can synchronize, share data, communicate.
But when we copy the memory from the host to the...
This is not this memory.
So it's an additional
Yeah.
level of memory.
Additional level of memory. Never talked about it before.
But you have operation. When you take this 7 data, you have to add them together to
Yes.
one
Yes,
new location.
that is true.
Now the nearby thread will have at the end another number.
Yes.
But it will see these 7, it will take what it...
I'm not talking about the operation. Only bringing it from memory. Only to read it once. I don't want to read each pixel 7 times. I want to read each pixel once from the input.
But each thread, when you cross it, let's say to the left, it will have one cell of data.
That is different. That is,
How
yeah, we will see how in a moment. But let's agree that it's wasteful to bring all 7 twice.
so maybe every 7 or 6...
We will see in a moment how it's done. We're only talking about concepts right now. Okay? Okay, so we're going to create a buffer of shared memory, and we're going to make the threads bring data into this shared memory, and then they can share the data. Okay? So let's see how it's done. This is the number of threads that I have in my block. So it's block dmax. This is the number of threads in the block. And in order to compute the output values for this amount of threads, I need to bring input pixels, 3 more on each side. That's what we said, right? So this is how it's done. This is actual code. What we do here is, this is the function definition, not surprisingly. This is the new keyword shared. And we are declaring a shared memory buffer of integers. The name of the buffer is temp, okay? And the size is block size plus twice the radius. Radius is 3. So it's the block size and the one radius on each side.
What is the maximum size of the shared memory?
It's maximum 48K. It depends on the platform. Okay, so we have a buffer. We've declared a buffer. Let's see what we do with it. We compute, this is G index is usually for global index. This is the index of the element in the input. So this is what we've seen before. Block ID x times block dmx plus thread ID x. This is the number of the element we're going to produce the output. This is the index of the output. And this is a local index that is only thread ID plus radius. We're going to see why we need it in a sec. And what we're doing here is we are loading, look at this line, single line, and it's loading all these elements. Look at this drawing here, it's very descriptive. This line is not loading just one element, it's loading all these elements into the shared memory. Why is a single line loading so many elements? Because it's parallel. Each thread has a different index, so it's filling in a different cell. So in one line of code, each thread went to the global memory, took an integer, and put it in shared memory. What do we want to do now? We want to put 3 more here and 3 more here. So not all threads need to work here, only 3, okay? So this is why there is an if here. Only threads 1, 0, and 2, smaller than radius, are going to bring 3 more elements here, and then another if, and we bring 3 more elements here. And right now what we've done is we've brought all the information that is required to calculate the output pixels for this range. 3 on the left, 3 on the right, and all the ones in the middle. So
How did it know to put the green boxes in the center?
it's my indexing. I did it. I started with this index plus radius. I did it. Okay? It's manual. If you do it wrong, it's wrong. So now I have everything I need in shared memory. How many times did I read each pixels? Once. Is that completely true? Did I really read each pixel once? Not completely true. Because another block, the next block, is going to overlap with my block a bit. So there's another block here and it overlaps with the pixels. But this is minor. It only overlaps a bit. Right? So how is this used? We finish bringing the data. And this is what we do to actually compute the sum. We go from minus radius to radius. And we go on the buffer. This is the shared memory buffer from the index and plus offset. So we sum from -3 to 3 all the elements that are around my center pixel into result. How many pixels did we add? 7. But how many times did we use the global memory here? 0. We did not access the global memory. We accessed the fast shared memory. Much faster. Okay? And in the end, you write the result out. So this is a single line of code. Why is it enough? Why is it calculating all the pixels, all the output pixels in a single line? It's parallel, yes, but what here makes it...
Index.
Exactly. This index is dependent on thread ID. So for each thread, this index is different, and therefore it calculates the output for a different index.
When you say global memory, you
RAM. This is the RAM
of the card,
of the card.
not the main memory.
No.
of the machine.
No.
Don't you have a race here?
Aha. So, this will not work. A wonderful thing. We've done a wonderful thing. We've only accessed the global memory the number of times that we really need. Not 7 times per pixel. Only the margins are slightly ineffective. But this will not work. And the reason this will not work is in fact really a data race. You have different threads bringing information. I'm thread number 0. Okay, well, in this I think they made a different example. Well, it doesn't matter what. Suppose I'm thread number 15. And I'm going to need the information to my right and to my left. And no one has brought it yet. How do I know that thread number 14 has finished? Maybe it didn't bring it yet. And also, the next one here, let's say the next one here, is one of those special halo pixels that you need to go through the if to get. And I'm not smaller than radius, so I jump here. Hello.
Hi, Oren.
Hello. I'll give them to you in 5.
Take your time.
So how do I know that the other thread brought the data it was supposed to bring to me? I needed to finish first to bring the data before I can use it. So this is a data race, and this is why we said that these threads can share information, but they also can synchronize. And what you have to do is you have to add into the code a function that is called sync threads. And what it does is after this code that we've seen before that brings the information into shared memory, you put sync threads, and what it does is it tells all the threads from this block, from the same block, to wait here until everyone has arrived. Only when everyone has arrived, we can continue. It's a very common bug to forget sync threads. Okay? Okay. So we don't have much time left, so I'll just sort of summarize this, and then I'll sort of summarize everything. The reason that we need threads and blocks is that threads can share information and help each other. We've just seen a way in which they help each other. We reduced the bandwidths of communication to the global memory, to the RAM, by a factor of 7 because the threads can share information they've brought. In other occasions, you can also share computations. A thread number 0 can compute something, put it in shared memory. We can sync threads, and then all the other threads can read it. This is also done. So the mechanism, the simplest mechanism, it's not the only one, the simplest mechanism to share information is putting it in shared memory and then doing sync threads. Only threads from the only threads from the same block can do that. And all the threads from the same block share the same shared memory and synchronize in sync threads. Threads from different blocks cannot communicate in any way. Okay?
Even not through the global memory?
They can communicate through the global memory. You have to manually do that.
So they can do that, but it's less efficient.
Much less efficient and much problematic for other reasons as well. That we,
Well, if you have shared memory, then you can synchronize.
Yeah, well, it's not so easy to talk about it because it's lengthy. But you can't really synchronize very easily between blocks, even in global memory, for some reason. There are reasons. Okay?
So what's the... Is there any overhead for the synchronization?
Yeah, of course there is an overhead, but what happens is this. If all the threads reach the sync threads sort of together, then the sync threads takes as much time as any other operation, as the simplest operation. If for some reason they are on different terms, waiting, and one of them is much slower than the other, then first you have to wait for everyone to arrive. So this is a complex issue. Leaving many things out. It's impossible to really say everything. But this is how threads can cooperate and sort of help each other do the same thing, whereas different blocks cannot cooperate and share and do anything together. Now, to sum everything up, I want to give you the briefest summary. GPU code runs on the GPU, but it is managed by the CPU. Okay? This means that all the administration code, mallocing, mem copying, calling the kernel itself is done on the CPU. The GPU does only the most compute-intensive operations. So first of all, you see what is your code is intensive, and only this goes into GPU. The part of the code that runs in the GPU is called the kernel. The kernel runs on the GPU. It is called from the CPU. Data is transferred from the GPU memory to the CPU memory manually. You have to do that manually. Once inside the GPU can be from anywhere from 5 to a few hundreds times faster than a CPU. It's more efficient per dollar, it's more efficient per watt, etc. The parallelism model is CUDA. In CUDA is this. Each invocation of the kernel creates the same code. You can't call different code on each core. This same code run on each of the cores. But those things that I call the magic variables are different each time, which enable us to create a different index, in which case that every core does the same thing, but for a different index of the data. This is the parallel model. The only reason that it's slightly more complicated is that these million of threads that are running together are not equal. They are divided into groups. Each group of threads is called a block, and the block, inside the block, the threads can cooperate, share memory. They can also ruin stuff for each other, right? If you can share, you can also destroy. So that happens. You forget sync threads. Try to forget sync threads, see what happens. So this is why we have these two layers of parallelism. Okay?
Can you run multiple kernels at the same time?
You can. You have to work for it, but you can. You can run multiple kernels at the same time, sometimes, and you have to work for it. There are more slides ahead. I'm not going to be able to go through them, but you take a look. It continues with this example with shared memory, and there is some stuff in the end about multi-GPU, error handling, stuff like that. Take a look. You have my card. Further help of industrial...
Now, what operations the GPU has, special operations? It can do multiply, it can do add or floating point, single precision, double precision
Yeah, sinus, cosinus, inverse tangents,
in hardware?
some of them.
What, you can do sinus and cosinus in hardware?
Some of them.
Which one?
Fast versions of them. Fast inaccurate versions.
But so because it came from graphics originally, so probably there are few operations that you have.
Okay, I can't answer.
From this
Yeah, I can't answer that, and I need to let everyone have a sip of water.
You can go on, it's okay.
An hour?
5 minutes.
Yeah. Okay. So I'm going to answer more generally. What we've focused on is the parallel model, and I hope you got that clear. What is the parallel model of the GPU? How you can program in parallel? But this last example with the shared memory and sync threads shows that it's not just that. Okay, it's not just the parallel nature, shared memory, sync threads. What else? And there is a lot of else. There is also a memory called constant memory and a memory called texture memory. And they are not easy to use, but they can give you really nice performances on some specific occasions. And there are also, your question, there are also other things that are implemented in hardware level. One example is if you work with images like I do most of the time, sometimes you need to sample a point that is a coordinate that is a fraction. And the GPU can do that very, very easily. Actually, in the same time it would take to just bring the point from an integer value. This is done in hardware, that's why it's so efficient. In the same way, other things can sometimes be more efficient. For example, if you have you need trigonometric functions, sinus, cosinus, some of them have a fast version. You don't write sinus, you write underscore sinus. And this has a fast implementation in hardware that is much faster, but is slightly less accurate. I can't go into all of these things, obviously, but the thing that you need to know is that they exist. These things exist. If you want to go into GPU computing and get full performance, there is a lot to learn about, for example, these things. I've also not really told you how these threads and blocks are mapped into hardware. If you want to write really effective GPU code, you need to know that as well. So I think in there, probably in the first part, you have all the links you could use. So in one of these links, you'll find everything you need. Okay? Thank you.